afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the latest video. Today we're going to take a look at past winter season analysis. In general, you look at the picture here on my cover slide. This was actually from the January 28th, 2021 snow that actually fell in Hampton Roads in Virginia, in southeastern Virginia. And it was the one and only accumulating snow of the season where the area received around 3 inches of snow. And yeah, this is really cool. This is actually something that was drawn in the snow, indicating when the snow actually fell. But in general, we're going to look at the past winter seasons. We're going to go back in this video to 2009, the 2009-2010 winter season. So let's get right to it. A lot of interesting things to discuss. So when we talk about the future winter forecasts, right, we need to take a look back at the past and see if we can decipher any clues from those past winter season analyses. So let's get right to it. For today's video, the agenda consists of, we'll first take a look at the U.S. winter temperature trends for December, January, and February. We'll look at the winter season teleconnection history, a review of past winter seasons dating back again, like I mentioned, to the 2009-10 winter season. So I'm going back just slightly over a decade in this analysis on this video. And then we'll take a look at key teleconnections and events shaping those past winters. First thing I want to start with in today's video is the temperature trends for the months of December, January, and February. This data courtesy of NOAA. We're starting off with U.S. December temperature trends. Anything with the red vertical bars above that 0% line, that indicates higher probabilities of past winter seasons of very warm winters or very warm Decembers. Anything in the blue bars below that 0%, that was basically the below normal winter seasons as far as temperature goes. So we're going back in these records to 1895, and you'll notice a fairly cold period there from about 1908 through about 1916. Then you get another very cold period around 1924, 1925. But then you get a very warm period there around 1940, getting colder again there around in the early 1960s. And then warm again, a warmer period again as we head into the early 1980s, followed by a very cold December back around December 84 and December 85. I remember that December 85 winter I really do remember that one quite a bit. I was in the Midwest at the time, so it was very well remembered in my mind. And very cold again there in 1986-87. But then, if you notice towards the right-hand side of the graph, how Decembers have been decidedly warmer with less blue bars there between the years 2010 and 2020. Looking at U.S. January temperature trends, again, very cold periods of time indicated by the blue bars, and that would be back in the late between 1915 and 1920, another very cold period again just after 1935 for January, 1950, back in the early 1960s, into the 1970s, the late 1970s, very cold Januaries. And then look at to the right of the graphic again and look at those red bars and how much above normal these Januaries have been recently. Especially, we're looking at 2000, looks like about 2007, and then 2015, 16, and 2019, 2020, very warm winter season. So we're trending towards warmer Januaries overall. February, U.S. February temperature trends. Wow, look at how much colder things were there around the 1900, early 1900s. And then how much warmer they were around 1930 in February. Again, there's a lot of ups and downs in this, right? The Februaries of the late 1970s, fairly cold. And then very warm periods there in the early 1990s in February. Also between 1995 and 2005, as well as the late, basically between 2010 and 2020. The Februarys have been very warm. Here's a look at the winter land surface temperatures across the entire northern hemisphere. So we're talking land. We're comparing this to the 20th century average. And this is in degrees. On the left, we have degrees difference from average in degrees Celsius on the vertical bar on the left. The vertical bar and the vertical there on the right is difference from average in degrees Fahrenheit. And so a lot of blue shadings there. This is going back to 1880. From 1880 to about 1915, we had some very cold, below normal, almost, a couple of those years, almost 2 degrees Fahrenheit below normal there, the far left part of this graphic, for the winter land surface temperatures in the northern hemisphere. Look how much blue it is all the way up through about 1920, even in 1930. Now look at the far right-hand graphic. Since 1980, look at how much above normal these land surface temperatures have been across the northern hemisphere. Really impressive stuff here. Anywhere from, I'd say, 1985, as I interpolate this graph, through about the year 2020. So we can see that we're trending towards warmer land surface temperatures as well compared to the 20th century average. Things are changing. The globe is changing. If I were to break this down closer to spot-on weather studios at Virginia Beach, okay, the Hampton Road cities, I chose Virginia Beach. Look at the graphic on the left. The data on the left is the coldest monthly and annual averages. And then on the right, I have the hottest monthly and annual averages. And the yellowish shading, those are the years generally going back to the year 2000. All right. So I only have three fairly cold values or years on the left for the coldest. 2015, February was the 5th coldest. The May of, what's it be? That'd be 6th on the ranking in May of 2005, 6th coldest. And then in December 2010, that was the 3rd coldest December in Virginia Beach, going back to when records began. And those records began back around 1876 for this area. Now, the graph on the right shows the hottest. Look at all the yellow shaded years on the right, including under the annual column. The number 1 warmest year in Virginia Beach was the year 2019. Number 2 warmest year, 2020. Number 4 warmest year, 2017. Number 5, 2012. 6th on the ranking is 2002. 8th on the ranking is 2016 for the warmest year in the Virginia Beach area. And number 10 is 2011. So if you look at the top 10 warmest annual year, basically years, top 10 warmest years, we have 1, 2, 3, 4, 5, 6, 7 of the last 7 of those hottest years for Virginia Beach have occurred since 2000. And 7 of those years go back to 2000 out of the top 10. That's really impressive. That's telling us something very, very important, right? It's telling us that the temperatures continue to get warmer and warmer. And then you can look at the individual rankings 1 through 10 for each of the months. So a lot of 2020s on there too on that graph on the right. A lot of very warm statistics for the year 2020 for Virginia Beach. So again, if you look at that graphic on the left under the annual column, let's see, the latest year it was a top 10 coldest year was 1904. No, I'm sorry, 1917. The 4th coldest year on record for Virginia Beach. But look at that. I mean, this really tells a story of how these temperatures are trending more and more above normal. Now, I'm going to go back now to some of the teleconnections history for the United States as a whole. And looking at this is average snowpack in the U.S. by winter. These are snow cover extent anomalies, all right? I have the years at the bottom of this graphic for the winter season. And you'll notice there's some notable changes from below to above normal snow cover extent. For example, if we go back to the 2010-2011 winter, the 2009-10 winter, we were generally above normal in the snow cover. All right. But look at some of the below normal extents too. It really appears that this graph is fairly cyclical, with above normal years, maybe the below normal season snow cover or snowpack slightly outweighs the above normal snowpack years. And this covers the period from December to February for the contiguous U.S., the entire contiguous United States. Looking at the Arctic oscillation history, I'll be mentioning this when the breakdown of the winter seasons. The blue bars on the graphic on the left indicate a negative Arctic oscillation. The red bars in the vertical indicate a positive Arctic oscillation. Now remember, negative Arctic oscillations usually correlate to below normal temperatures across the eastern United States, whereas the above normal or positive AO equates to above normal temperatures for the east. And so, looking at the graph on the left, you kind of see we had a fairly significant negative AO back in the 2009-10 winter season. We had a very strong positive AO exceeding magnitude 2.0 there in the late 1980s. The graphic on the right is just kind of a summary of the standardized 3-month running mean or average AO index through August of 2021. Again, the blue spikes on the graphic on the right indicate negative AOs, and the red spikes pointing upward indicate positive AOs. So there's a lot of ups and downs in the Arctic oscillation. Just wanted to kind of give you a feel for how these trends occur and what they look like. For the North Atlantic oscillation, the NAO, the history, again, the blue bars indicate negative NAO. The red bars on the graphic on the left indicate positive NAO. Positive NAOs are generally associated with warmer than normal temperatures across the eastern United States. Negative NAOs are associated with big Greenland blocks in the North Atlantic, and that tends to buckle the jet stream into more of a trough configuration upstream of that huge ridge into Greenland, which generally leads a negative NAO to much colder than normal temperatures for the eastern United States. So anytime you see the blue bars pointing, kind of going downward below that zero value, that generally indicates we had a very strongly negative NAO, for example, in 2010 winter season. A fairly strongly negative NAO there around 1969, but then strongly positive NAOs in around 1989, 1990, and again between 2010, really the decade between 2010 and 2020, if you look at the graph on the left, really influenced a lot by positive NAOs. If you look at the graphic on the right, it's a standardized 3-monthly running mean NAO index through August 2021. Again, the blue spikes indicate negative NAOs, and then the red spikes upward indicate positive NAOs. Again, blue NAOs, the negative NAOs or the blue colors indicate below normal temps in the east, and then those red positive NAOs generally indicate milder conditions for the winter season. Looking at the El Nino Southern Oscillation ENSO history, looking at the multivariate ENSO index version 2 on the left, this goes back to around 1980 or just prior to that, generally showing the red spikes indicate El Nino years, the warm version of the ENSO, and then the blue spikes in the negative territory on the left indicate La Niñas. So we have red spikes El Nino, warm episodes. Blue spikes below the zero line down in the negative territory indicate La Niña, colder, not colder, but necessarily cooler water temperatures in the east central Pacific. Looking at the graphic on the right, the data table there, courtesy of NOAA, you can go to the Climate Prediction Center site and get this great information. You'll see the values, the departures from normal of the water temperatures in the El Nino 3.4 region across the equatorial Pacific, the eastern Pacific. In general, you see the value and the magnitudes by the numbers. The blue numbering indicates La Nina years, and the red numbers indicate departures from normal, and generally they indicate El Nino years. Now, if it's just a dark numbers generally indicate ENSO neutral times. So this goes back, the data on the right, from the year 2000 to the year 2021. And really looking at the color shading of the numbers, You know, it's pretty evenly distributed. In other words, I don't see a trend in which, you know, we're having more dominant El Nino seasons versus La Nina. So really, you know, we went to a La Nina winter last season back in July, August, September timeframe, and then that increased in magnitude to a negative 1.3 last winter season in October, November, December, to negative 1.3 value. And then it kind of came back up again. So it wasn't a super strong La Nina last winter. It was more of a weaker La Nina. But the latest forecast by the Climate Prediction Center does indicate La Nina to return for the upcoming 2021-22 winter season. Here is the Pacific North American pattern history, the PNA, showing you the standardized 3-month running mean PNA index through August 2021. The red shading indicates, those red spikes indicate positive PNA periods, and the blue negative PNA periods. So the positive PNA periods, again, just as a reminder, correlate to a ridge, an upper level ridge over the western U.S. and western Canada, with colder temperatures over the central and eastern U.S. and a trough, while the blue shading, the negative PNA, is the opposite. You get a trough in the western U.S. and a ridge in the eastern U.S., so much cooler temperatures in the west and much milder temperatures across the eastern U.S. during the winter season. So this is always useful to take a look at. Just kind of look at the years where, you know, we were dominated more by positive PNA patterns. One of the more recent ones I can think of is the 2014-2015 winter season, where we had that ridge, upper level ridge, it just sat over anomalously warm water temperatures in the Northeast Pacific all winter long. All right, so now we're going to delve into the specific winter seasons and talk about the different influences from the winter seasons. We're going back to 2009-2010 winter, and when I say winter in this video, I'm referring to the months of December through February, otherwise known as meteorological winter. So let's start off with 2009 and 2010. By the way, these graphics for the globe, as far as departures from normal, are courtesy of World Meteorological Organization. The Climate Explorer is where I pulled these charts. Great website if you got some time to take a look at it. Also, I want to just introduce you to the chart on the left. So we have the red shading generally indicates above normal temperatures. The blue shadings are below normal temperatures. All right. And then the graphic on the bottom there shows how far off these temperatures were in degrees Celsius, the departures from normal. If you see a white shaded area on these graphics, it generally indicates near normal temperatures. All right, so this winter in particular, December 2009, February 2010, this was influenced by a splitting stratospheric polar vortex, a record-breaking negative Arctic oscillation, and a strong El Nino year. So we had a lot of what I referred to in last week's video as destructive interference. Destructive interference occurs when one of the teleconnections or another, maybe you have two teleconnections, are working against another teleconnection. Okay, so in this season we had destructive interference where we had a weakened polar vortex and a negative, strongly negative Arctic oscillation. All right, to counter that, we have this strong El Nino pattern. So the weakened stratospheric polar vortex and the negative AO, these were huge climate drivers during this particular winter season. You see much below normal temperatures there on the graphic on the left over Siberia, into parts of Europe. You got much colder, you get colder than normal temperatures there across the Midwest into the eastern U.S. Here was a look, the source is Pavel Vargin. This is the December 2009 polar vortex split in the stratosphere. So we're showing a time lapse basically between point A there on the upper left to point D in the lower right of this slide, and showing the darker shading generally indicates the polar vortex. This is up at 10 millibars, well above where we live here on the Earth's surface. But you generally, at point A in upper left, you generally have an elongated polar vortex. By point B, on the 10th of December 2009, that polar vortex now is getting stretched. It's stretching out, it's weakening, it's been displaced off the poles, And at point C there in the lower left, you now have two specific polar vortex lobes that are existent. One is over Northern Europe and the other one is over Canada, over North America. And then at point D on 18th of December 2009, you have that vortex impacting a lot of, that lobe of the polar vortex impacting a lot of people. Additionally, we have this strongly negative Arctic oscillation. If you look at the blue bars on the right of the graph there, look how far in magnitude those bars go below the zero line. Basically from mid-December through mid-January. We had very strongly negative Arctic oscillation, which favors much colder than normal temperatures across anywhere from the Midwest to the East Coast of the U.S. And you notice all those bars, magnitude down to -4, record-breaking Arctic oscillation. And as a reminder on the right, the AO relationship to the stratospheric polar vortex, when the AO is positive, where those blue bar lines there on the left are above zero, when it's positive, the polar vortex is usually stronger and it's centered over the North Pole. It's more of a circular shape, symmetric, keeping all the Arctic air bottled up over the poles. Now when the Arctic oscillation is negative like it is there in 2009-2010 winter season, then the polar vortex weakens, leading to a more meridional or wavy polar front jet stream with much colder air masses that move into the middle latitudes. Additional factor in that winter is we had this strong El Nino. You see the writing there, strong El Nino on January 4th, 2010. That orange and yellow shading indicating temperatures much above normal across the Nino 3.4 region, the eastern equatorial and central equatorial Pacific Ocean. So let's take a look at what happened with the actual sensible weather. This was a year of snowmageddon. If you lived in the northern mid-Atlantic states, especially the Washington, D.C. area, these are 4 specific storms that impacted you really strongly. You see the, starting off on the left with December 2009 North American blizzard, moving over to February 5th and 6th, 2010, another blizzard. A few days later, it was February 9th and 10th, 2010, we had another North American blizzard impacting the northern mid-Atlantic. And then February 25th to 27th, 2010, another blizzard. So this was a very busy nor'easter season along the East Coast. A lot of great dynamics were in place with that amplifying, deepening trough, with that negative AO in effect. I remember this storm specifically on the left, the December 2009 storm. I remember traveling from Virginia to the Midwest, and I have not seen snow fall quite that heavily. Interstate 64, basically from Hampton Roads through Richmond, and then once you got west of Richmond, it was all heavy snow. The Interstate 64 was completely snowpacked, like I was driving on a country road. I was fortunate that night to get a hotel out towards Staunton and Waynesboro in the western part of Virginia. And it was, oh boy, I think the snow rates on that storm were probably 2 to 3 inches per hour. And so I remember that one specifically on the left. The other systems in February was just super active. Very, very active winter season for snow across D.C. These are some of the statistics there beneath these satellite images of the various storms. Just really interesting. And some of these barometric pressures, 968 millibars with that December 2009 blizzard, 978 for the early February 2010 blizzard. Very low pressures. Now we're moving on to the December 2010, February 2011 winter season. You'll notice on the left we have much above normal temperatures across northeastern Canada into Greenland, also across the far Pacific side of the Arctic. We had below normal temperatures from the northern plains to the east coast of the U.S., as well as across Norway, Finland, Sweden, into parts of central Siberia. So this particular winter was influenced now by a strong La Nina, the opposite of El Nino. We had a negative NAO with increased frequency of high latitude blocking over the North Atlantic, And you can see we had a very strong ridge. It was above normal, that red maroon shading there in the Greenland. That just tells a story right there about the blocking that was going on with that negative NAO that winter. Here was the strong La Nina in December 2010. This thing completely reversed, right? From a strong El Nino in January 2010 to a strong La Nina in December, just 11 months later, the same year. You'll notice the blue shading there, right where the word strong La Nina are. That generally indicates much below normal temperatures across the equatorial, eastern, and central Pacific. Look at the negative North Atlantic oscillation. A lot of high latitude blocking on the North Atlantic side during this winter season. You'll notice how far below those blue bars go, below the zero value line there in the negative territory. Really started getting very strong, in excess of -2 magnitude for the NAO just in the last week or so of November, and it remained a fairly negative NAO winter on all the way up through just shy of mid-January. Looking at one of the major events of that winter season in 25 December 2010, right, was this snowstorm for southeast Virginia, and then it went up the East Coast into parts of New Jersey, New York City, parts of Massachusetts. I was out of town for this storm, actually. I missed it here in southeast Virginia. But this thing brought some of the greatest snowfall totals for Norfolk. You look on the right-hand side there. We have an individual event total there on the left graphic. And then on the far right graphic, you have the daily total for snowfall, the record events for Norfolk, Virginia. And this 2010 storm, December 25, 26, if you look at that, 14.2 inches of snow fell across Hampton Roads, Virginia. And then on the right, you look, and for the daily total, 13.4 inches fell in a 24-hour period on December 26th. This thing clobbered. It's a Nessus 4.92 Category 3. You see the blue shading there, the lighter blue shading there, indicate 10 to 20 inches of snow anywhere in that lighter blue shading. This thing was a very intense, what referred to as a bomb, deepening, very strongly deepening cyclone. A bomb is referred to as a cyclone which deepens by 24 millibars in a 24-hour period. This thing was a beast and impacted quite a bit of real estate across the East Coast of the United States. I remember coming back into town, and that's the snowfall. It was just incredible how deep it was. Moving on to December 2011, February 2012 winter season. Very mild and dry for the Mid-Atlantic and the eastern U.S. You see the orange shading there, extending from generally western Canada, stretching southeast towards the Great Lakes, Midwest, all the way across New England, down through the southeast and the Mid-Atlantic. It was a warm winter, this one. If you look across the Pacific side, over in the Arctic Ocean, look at the darker shadings of the maroon colors there. Very much above normal in the Arctic areas on that side of the world. And then you had below normal temperatures over Siberia, the western parts of Siberia, back towards Russia on this winter. Looking at U.S. temperature and precipitation departures that winter, look at how mild or above normal it was. That's in degrees Fahrenheit, by the way, the scale on the left. Just showing how warm it was. 10 degree Fahrenheit, in excess of that, as far as the winter, December to February went that winter, across North Dakota into Minnesota. And then the precipitation departures were on the right. It was very dry across the Mid-Atlantic, on down the southeast coast into the Carolinas and Georgia into Florida. It was a very dry winter, 2011, 2012. It was a very mild, dry winter. Now we're moving on to December 2012 to February 2013. This was a wet and mild winter across the eastern U.S. You're looking at the global temperature anomalies on the left in degrees Celsius. Very cold over central and eastern Siberia. But again, that warming continues across parts of the Arctic Ocean area there, north of the Siberian continent. And then you have warmer temperatures in this particular winter across the eastern U.S. up into New England, up into parts of northeastern Canada towards the North Pole. Here were the precipitation departures from normal for that particular winter. Fairly wet this time, generally east of the Mississippi River, and then dry, very dry in California. You can see the brown coloring there, indicates very dry times. Moving into December 2013, February 2014, this was a very interesting winter. I was living out in San Diego at this time, and we had a very mild winter, and it was dry out there. But I just kept hearing the reports, the weather reports across the United States on the news, and wow, we had a weakening polar vortex that winter. We had record-breaking cold across the eastern U.S. Between 6 and 10 December. Close to 100 daily snowfall records across the northeastern, southeastern, and south central U.S. The coldest air to affect the central and eastern U.S. in 20 years. And we had a El Nino southern oscillation with ENSO neutral conditions with a strongly positive PNA. So we have a very strongly positive PNA. That means we've got a huge upper level ridge over the western U.S. and western Canada with a downstream trough just directing extremely cold air from the high north, specifically northern Canada, down into the Midwest and eastern U.S. This polar vortex disruption, wow, this was a good one. This was in January, early January of 2014. The map on the weather chart on the left shows January 6, 2014. The bluish arrows indicate the direction of extremely frigid Arctic air, a direct connection to the Arctic into the U.S. The general 498 ring there on the left, that circular area with the 498 value, extremely low atmospheric heights associated with very frigid polar air, and that's the vortex lobe right there. The graphic on the right was a 500 millibar. These are height anomalies, very much below normal heights, extremely low. The green shading on the graphic on the right shows the circular nature to the polar vortex lobe just coming down the center of that thing, generally over Lake Huron into the upper parts of Michigan. And this was just a frigid air mass in early January 2014. How frigid was it? Look at the graphic on the right in the U.S. These were the wind chills. These were the wind chill values in early January of that year, in early January 2014. If you were to step outside in Chicago, it would feel like negative 42. You step outside in Minneapolis, Minnesota, it would feel like negative 45. The very, right around Duluth, negative 51. I mean, the wind chills, look how far south they go. It felt like 0 degrees in Arkansas, 7 above 0 in Mississippi, 12 degrees above 0 in Atlanta. The graphic on the left shows the overall temperature anomalies during January 2014 with the blue shading well below normal temperatures. The darker the shading, the much more below normal these temperatures actually were. The pinkish shading indicates above normal temperatures, and you could just see how cold it was. The direct connection of January 2014 from the Arctic all the way down to the Gulf Coast. The eastern U.S. was frigid. Northern Siberia into parts of Europe, especially Eastern Europe, was frigid as well. So that was quite an interesting winter. That then leads us into December 2014, February 2015 winter. Not as frigid as the previous winter season. And you'll notice too now, the northern Siberia area has now been replaced with warmer temperatures. I did skip a slide. I might have gone too quick. Just to wrap up the winter of 2013-2014, let me just mention this. This was a very important factor in developing that positive PNA and that long wave ridge, upper level ridge over the eastern Pacific Ocean. The graphic on the left shows sea level pressure anomalies in millibars or hectopascals on the order of +6 to +8 millibars above normal for that time of year. And then the graphic on the right shows actual sea surface temperature, the water temperature anomalies in degrees Celsius almost 3 degrees Celsius above normal there in that center box on the graphic on the right. So we have this huge pool of warm water. They sometimes refer to this as a warm blob. And that, the atmosphere, ocean, they interact together and they're connected. And sometimes what you get is this unusual warmth in the water temperatures, which then equate to unusual configurations of the polar front jet stream. In this case, the whole Gulf of Alaska from the Northeast Pacific, there was a huge ridge with a very deep trough directing much frigid Arctic air east of the Mississippi River during this particular time period from December 2013 through February 2014. I wanted to show you that. I think I skipped over that. I went right over it. Now, turning our attention to December 2014, February 15 time period, that winter, it was frigid across the eastern U.S. from January through March. The stratospheric polar vortex weakened, with a lobe of extremely cold air pouring south into the eastern U.S. For example, a place like Pensacola, Florida on the Gulf Coast dropped to 28 degrees by 19 November. Frigid. Boston, by the way, broke its all-time seasonal snowfall record with 108.6 inches of snow for that particular winter season. I mean, they just had storm after storm up in New England for Boston. Just piles high of snow up that way. It was a very active nor'easter season with frequent coastal storms as well. Here were the U.S. temperature departures overall for the winter. You see the pink salmon colors generally out towards the western U.S., and then the blue shading indicate the below normal temperatures from the Midwest to the East Coast, all the way down to the Gulf Coast. So it was a colder winter again across the East. Moving ahead now to December 2015, February 2016 winter. Winter was influenced by a strong El Nino. It was one of the warmest Decembers on record for New York City. It reached 70 degrees on Christmas Eve. And I remember this one particularly well because, here in Hampton Roads, Southeast Virginia, we had back-to-back 80-degree high temperatures Christmas Eve and Christmas Day. It was insane. You could wear shorts and a t-shirt on Christmas, and it was just well above normal for that time of year. We're talking 25 to 30 degrees Fahrenheit above normal. This was the warmest winter on record for the U.S., by the way. And it was one of the coldest periods occurred around Valentine's Day 2016. It was one of the rare cases where it was colder than normal. Boston's temperature dropped to about negative 9 degrees Fahrenheit with a negative 36 degree Fahrenheit wind chill value. But, look at the Northern Hemisphere as a whole. Very warm above normal. Look at the Arctic Ocean again, well above normal. Just not much blue shading for the winter of 2015-16. This was a really warm one. Here were the U.S. temperature departures for that winter, 2015-16. Look at the whole U.S. I mean, you're near normal in parts of the western U.S. there, in Utah and Nevada. But, wow, what a warm winter this one was. Now, December 2016, February 2017 winter season. Let's take a look at that one. This was a warm winter across North America as a whole. We had a weak La Nina. We did have a notable winter storm that brought snowfall to the southeast and mid-Atlantic states in early January. It was really the only bout of winter weather that we saw that year. This was the snowstorm from 6 and 7 January 2017. Southeast Virginia. We got hit pretty good in Hampton Roads cities on this one. You see that purple shading there? That indicates 10 to 12 inches of snow. And the lighter blue shading indicates 8 to 10 inches of snow, and the darker blue shading indicates 6 to 8 inches of snow. So this was a good one. It went up through Philadelphia as well, just to the southeast of D.C. I mean, D.C. did pick up a couple, 2 to 3 inches of snow out of this one. But in general, this was more of a southern mid-Atlantic storm up to New Jersey, Philly, that area. Moving ahead to December 2017, February 2018 time period, there was a very erratic weather pattern across the U.S. this winter season. There was a rare snowstorm that affected the southern U.S. in early January. Now that storm, it was interesting. Savannah, Georgia got hit with snow. Charleston got hit with accumulating snow. Southeast Virginia, I remember that one. That was a really heavy snow for Southeast Virginia and Hampton Road cities. An outbreak of frigid air affected the U.S. in late December and early January. That really set the table. If you want a good snowstorm across the mid-Atlantic, you want some frigid air to really lock itself in place prior to a storm coming up or arriving from the southwest, that moisture. We had a series of strong nor'easters which impacted the northeastern U.S. that winter as well. And there we go again, a common theme, a weakening of the stratospheric polar vortex in December. A parade of nor'easters moved up the East Coast through March. So let's take a look at this. Starting off with that late December 2017, early January 2018, showing land surface temperature anomalies on the left in degrees Celsius. Look at all that blue shading. That darker blue shading over Illinois, Indiana, Ohio, into parts of West Virginia and western Pennsylvania, that's land surface temperature anomalies in excess of 15 degrees Celsius. Meanwhile, the West Coast was well above normal, but you generally see what we had going on late December and early January. We had cold setting the table, and then we had a major storm there on the right. The graphic on the right shows a weather satellite of that extremely deep storm system, low pressure area, that nor'easter. The pressure got down to 949 millibars. If you were to look at your pressure dial at home on your barometer, that'd be 28.02 inches of mercury. Just incredible. This storm was, like I said, blizzard warnings in Virginia Beach. I remember this one well. Up to 10 inches of snow with the winds. The drifts were up to anywhere from a foot to 16 inches high. And quite a damaging storm as well, with $1.1 billion in 2018 US dollars. December 2018 to February 2019, extremely cold air, initially located over the upper Midwest to Great Lakes. It generally retrogressed back, moved back westward toward the northern plains in February 2019. This was a very disappointing winter for the mid-Atlantic states. Very mild, I don't remember any snow in this particular winter, actually. Now, we did have a major, another polar vortex disruption in late January of 2019. The graphic on the left shows 2-meter temperature anomalies in degrees Celsius for January 29, 2019. And you see that those purple shadings, extremely frigid air. And look at how it goes all the way up to the North Pole. This connection from the North Pole all the way down into the upper Midwest of the United States. Look at those wind chills on the right. Just phenomenal. These were the wind chills at 5 a.m. Central Time, ending on Wednesday, January 30th, 2019. Places like Chicago, wind chills approach negative 55 degrees Fahrenheit at night. Places like Milwaukee and Detroit, negative 55 at night. Unbelievable. Record-breaking extreme cold across the Midwest and Great Lakes as the polar vortex collapsed. And we got that direct Arctic connection, but just phenomenally cold. This cold, with this particular polar vortex weakening, what was interesting, it never really made it completely to the East Coast. It started over the upper Midwest here, as you can tell on these wind chill values on the lower right. But then all that really extremely cold air backed up westward, retrogressed, back towards Montana into the Dakotas area, and just sat there the rest of the winter with extremely cold air. December 2019 to February 2020, we had ENSO neutral conditions. We had a record strong AO, Arctic Oscillation, which, wow, this was a very mild winter. I can remember New Year's there in early January of 2020. It was probably 76, 77 degrees for a high, when the temperature should be about 48, 49. 30 degrees above normal temperature marchers across southeast Virginia that winter. And I mean, look at the graphic on the left. Look how warm it was across Europe, Siberia. That's where the heat of the winter was focused. Just unbelievable. Alaska was colder than normal this winter. But this overall was the 6th warmest winter on record for the U.S. The 2nd warmest winter on record for the entire globe. A record strong polar vortex. It kept the coldest air bottled up over the Arctic. Extremely positive Arctic oscillation as a result. February was especially warm. Very warm across Europe and Asia. 11 degrees above average in Europe and 18 degrees above average in Siberia. Just phenomenal. The average temperatures in Moscow, Russia were 32.3 degrees Fahrenheit. This was 11.3 degrees Fahrenheit above normal for that winter. Additionally, in Helsinki, Finland, no snow fell in January or February for the first time on record. So this was a very warm winter. These were some of the precipitation departures in February 2020, just to give you a sample of the winter. Brown shading indicates below normal precip. Look at California. Jeez. Super brown on the shading. Very dry conditions in February 2020 for them. And then you have a lot of greens or above normals across Mississippi, Alabama, and Georgia in the southeast, eastern Tennessee, on up in eastern Kentucky and western Virginia. There was a lot of rainfall in that particular month in 2020. Here is the record-strong polar vortex 2019-20. The purple shading generally indicates the position of the polar vortex. We're looking down, strictly down, straight down over the North Pole in this particular slide. You see the purple shading with the white arrows. Look how symmetrical or circular in shape the polar vortex is, and it just sits. It was extremely strong, and it stayed right over the North Pole the whole entire winter. There was just no disruptions of the cold air to come south into the mid-latitudes in the U.S. So, very, very warm winter. And then finally, December 2020 to February 2021. Note the excessive warming, the maroon shading over northeastern Canada into the Arctic regions, with high latitude blocking into Greenland and northeast Canada. Last winter, there was a lot of negative NAO. There was a very strong North Atlantic block in place, a huge upper level ridge into northeastern Canada, into Greenland. In February, extremely cold temps. We'll never forget this one. Extremely cold temps took a dive into the southern plains, including Texas. There was a very wet pattern set up from the southeast and the mid-Atlantic in February on the leading edge of that very cold Arctic air. The contiguous U.S. in February temperature was the coldest February since 1989 and the 19th coldest since records began back in 1895. So, this, you see a little bit of blue shading there over the southern plains there on the graphic on the left. And that was mainly due to the extremely frigid February. What caused that? Well, our friend the polar vortex again. Wow. The polar vortex split into two distinct lobes in this case last winter. Let me start with the graphic in the upper left, that purple shading. That graph in the upper left shows a number of hours that were below freezing, below 32 degrees Fahrenheit over the week from February 12th to the 19th, 2021. And look at the purple shading and how far south that went. All right, we're talking 144 hours or 6 days straight in Texas, where the temperature never got above 32 degrees Fahrenheit, never got above freezing for 6 straight days. The graphic on the upper right, that shows the lowest temperatures that were forecasted for a Sunday through Tuesday period during that time period. Low temperatures below zero all the way down to the Texas Gulf Coast. Just unbelievable how cold the air was with that particular polar vortex weakening and coming off, getting displaced off the poles. The bottom left shows that disruption of the polar vortex in early January 2021. The far bottom left graphic shows the polar vortex getting stretched on December 26, 2020. By the time we get to January 5th, 2021, we had extreme warming of temperatures in the stratosphere, that sudden stratospheric warming event, which weakened the polar vortex. And then bottom right graphic there shows January 15, 2021, the purple shading, how the vortex is split into two distinct lobes. And the bottom right-hand graphic shows snowfall. Snow on the ground in Houston, are you kidding me? San Antonio and Dallas, just unbelievable. Down into parts of Mississippi, Louisiana. These are places that very rarely see that kind of weather. And it was all because of the polar vortex and the stratospheric warming event that occurred in January. Now keep in mind that the sensible weather effects from these polar vortex weakenings, whether it's a stretching vortex or a split vortex, it generally takes 30 to 40 days for the weather to actually become much colder. Those effects will be felt after the vortex weakens. So here are the final thoughts on today's video. we look back at a lot of winter seasons, highlighting some of the main points of the main climate drivers that influence those seasons. There's many examples of these winter seasons where we had teleconnection, constructive and destructive interference. Now, as a reminder, constructive interference is when the teleconnections kind of work together in the same direction and produce amplifying effects. Destructive interference is when you may have one teleconnection indicating one thing and then another teleconnection offsetting that. Overall trend is for warmer winters across the Northern Hemisphere. We see it. We saw it at the beginning of this presentation. Let me go back to it real quick. By looking at these graphs, these figures, they tell the truth. And look at how those red bars on the positive side, above normal temperature departures, have become more frequent, especially since about the year 1990, the 1990 to the 2020 season. Look at these graphs here, just the individual winter time months, December, January, and February. They all tell the same story, that the winters overall, the land temperatures are getting warmer and warmer. Okay, next we're going to talk about, we're seeing more in the way of a weather pendulum. What do I mean by that? The winter seasons are swinging from one extreme to another on shorter time scales. So for example, we may have one winter where we're very warm, 3 to 4 degrees Fahrenheit above normal, followed by the very next winter where it's below normal. Okay? And so the Earth, the atmosphere, is responding to the accelerated warming caused by global warming. And so we're seeing this weather pendulum where these winter seasons are swinging back and forth from potentially extreme cold with polar vortex disruptions to extreme warmth, where we're seeing hardly any resemblance of a winter that we used to see. The episodes of extreme cold, however, they do appear to be limited on a temporal or time scale. When we get these polar vortex disruptions, they generally occur on maybe a 2 to 3 week time period. And so we're not seeing longer lasting extreme cold, right? It's very rare for us to have extreme cold from early December through late February in many parts of the country, in the U.S., or across the globe for that matter. So the episodes of extreme cold appear to be associated with that weakening polar vortex, but again on a limited time scale. Winter weather, it's starting later and later. It seems like winter is starting later and later each year, and there's been research on this, and it seems that winter weather is extending further into the spring months, March and April now. So maybe with global warming, the future winter season may go from early January to late March. It seems like these seasons are shifting, if you've noticed it. And then disruptions. I wanted to mention this. Disruptions of the polar vortex. Look at this. They've occurred in 4 of the past 10 winter seasons, resulting in abnormally cold air moving towards the mid-latitudes, whether it's Europe, whether it's Siberia, whether it's North America, the U.S. Last year with the Texas extreme cold outbreak, just proof of how important the polar vortex really is in the weather during the winter season. The Pacific jet stream, just as important. What are the water temperature anomalies across the Pacific? Is the jet stream from the Pacific extremely strong? Is it oriented more west to east to where milder Pacific air dominates the United States winter season? Or do we have a case where we go back to this particular season in 2013-14, where we get a polar vortex disruption, and we get unusually warm water temperatures, sea surface temperatures in the Northeast Pacific, setting up anomalous ridging across the Northeast Pacific, an extremely positive PNA pattern, where we get this huge ridge. What is a jet stream configuration? That has to do with everything with the actual sensible weather we experience in the winter season. So just a thought. Okay? So these are our observances or observations that we've noticed over the last 10 seasons of winter weather. One thing for sure we can note that's not put on there as a bullet is simple. Look at the maroon shading in almost every one of these past winter season analyses. Those above normal temperatures, the maroon shading on the order of 3 to 5 degrees Celsius above normal. Where is that typically occurring the most? In the Arctic areas. Here's this particular winter season. We'll keep going back. Oh, look at that one. In this particular season, a record warm year, the globe in general, in the Northern Hemisphere. Look at this. I mean, look at Europe and Siberia in that particular winter. But look at the theme. You got to look at the trends. Where are the warmest winters occurring? And the answer is the Arctic. Okay. The Arctic just isn't getting as cold as it used to be, and that's going to have long-term implications on our particular atmosphere, and the atmosphere is going to respond the best way it knows how. It's going to try to figure out ways to mitigate this extreme warming. You know, when you're warming an area twice as fast as the rest of the globe, you get all this ice melt. It's incredible to watch how things unfold, how the atmosphere responds to that. So I would feel that in future winters, we're going to continue to see this weather pendulum with this Arctic warming, where we're going to go from, this could even happen during the same winter season, where you go from 70 degrees one day, extremely above normal, to, 38 the next day for a temperature, very cold the very next day. Or maybe it fluctuates on a temporal or time scale of 2 weeks are extremely cold, swings dramatically to extremely warm for the next 2 weeks after that. We're going to see more of winters like that. So past research done by Dr. Judah Cohen, again, indicates the global warming could be leading to higher frequency of polar vortex disruptions, which could actually do the opposite effect of what we think global warming would do, and that would be with these polar vortex disruptions more frequent, adding more extremely cold episodes to the United States and Northern Hemisphere winter period. Just real interesting stuff today on the video. I hope you enjoyed it, looking back at some past winters. We really appreciate the subscriptions. Look, I'm very appreciative of everyone who follows Spot on Weather here on the YouTube channel. We got so much to look forward to coming up too. I'm so excited. I'll be getting into some other interesting videos involving the winter season, as well as the teleconnection discussions, most likely looking to start that around the 8th of October, the teleconnections discussions, the weekly ones, as well as the winter weather forecast. And I really enjoyed putting that together. I was laughing at the Farmer's Almanac because it actually says it's going to be an extremely cold winter in the United States. I take all that with a grain of salt because we really like to delve in here at Spot on Weather on the science, the analytics behind past winter seasons. What are the indicators this winter season from, the sea ice extent in the northern oceans to, the phases of the El Nino. We have to look at all of that and take it into account. So looking forward to it. Thank you so much for watching this video. Wishing everybody a safe and healthy time. God bless everybody. Take care. That is all for now from Spot on Weather.